recording now. Alrighty. And let's pull that down. I'm gonna got a mic on. Hold on. Okay. Or unless you want to say something, I'm really sorry. You can unmute yourself if you need to talk to me. Is I don't want people to accidentally have their mics live. Okay. I think we're good, guys. Let me go into present mode. Y'all can still see me, yeah? Okay. Chat. Yes. Cool. All right, guys. Oh, that was not supposed to happen. Okay. Welcome everybody to the first Rocket League meeting on the online version. I appreciate the patience. It's been really weird this year. I'm trying to get back on campus, but ending up having to do a mixed mode version. Just a little quick explanation. Basically, we got a room on Tuesday, but UCF never gave us a room for Thursday. Even though we requested it, they never gave it to us. So I decided, he sent the attendance form in the chat. Oh, there should be a link later. Also, there's this link here. Though honestly, the attendance form isn't the biggest deal for me. As long as you guys get the content at some point, and also the first meeting, it's a lot of very basic background information, but it's not so much the actual designing and building stuff. It's to get you primed and ready to understand how the rockets work. So yeah, no, but anyways, back to the rooms thing. We didn't get a room for Thursday, even though we requested it. So I made the really quick decision. Let me just do an online version. So I have this mixed mode now. So here we are. Welcome everybody. And I'm going to start moving on to these slides. Let me just click. Cool. So today's agenda, I'm just going to go over the office hours, the leads, what the project's all about, the scoring / objectives. I'll do more later. The tentative schedule, launch day info, stability, and any questions you all have. You'll have time to ask. So first of all, office hours. Long back before COVID times, there used to be dedicated office hours where, basically at the TI lab or something, you can find one of the officers for Rocket League and ask them questions about your rocket. We don't do that anymore. We stopped doing that because COVID, we couldn't be on campus. So now what we do is we do it all on Discord. So if you're designing or building your rocket and you have any questions, you can just DM one of the leads. And when you're in your teams, you'll be assigned basically a lead who will help you out. So you can talk to them or really just talk to anybody. We'll all help you out and have your questions answered just in Discord DMs. Please don't use the email. I know we put this here, but we don't check it very often. So you're definitely going to have your best chances of talking to us just on Discord DMing us. Moving on about us, that's me. I'm Brian. I've been here for quite a while. I'm a senior and this is my last year here. I've done rockets before. Gold Division is the Lander Challenge now, which I'll explain more later. That was a very interesting project. And also I have my level 1 certification that's to do high power motors. I'll explain motors and stuff later today. So I know my way around rockets. This is Mark. This is the other lead. I've been working with him since last year. Very similar experience that I have. So he's definitely doing very well. We also have Keithan. He's one of our newer assistants. He's going to help us out this semester with helping you guys with your rockets and also leading up on the project. Unfortunately, one of our leads did not put down his information. So yeah, it's fine. We'll just move past the about us. But yeah, no, if you need to contact any of us, just Rocket League chat, or you'll just find us in the Discord, just labeled as lead. And you can just ask us questions. So about the project, this is just a 1 semester long, 4 to 5 weeks. You're going to understand what rocket science is, how to use OpenRocket, which is basically a program that allows you to design your rockets. It's really easy to use. There will be a different lesson dedicated just for how to use OpenRocket, so don't worry quite yet about what that actually means. You also learn SolidWorks. That's a very big thing in UCF. For anybody who is a freshman here and an intro to engineering, chances are you're going to learn, at least in a rudimentary level, how to use SolidWorks. And we're going to help you use that, not to make something this sophisticated necessarily, but all your wooden components will be put in SolidWorks so that you can get it laser cut. And you will be working in teams. So, there's a collaborative effort. Working in teams is very important in engineering. I'm now in senior design, and that could not ring more true. Having to get a team together to work on the same thing. I'm actually building a rocket for my senior design project, funny enough. So yeah, that's what the project's all about. The competition, it's the way that it is that there's 3 different sections. So the first is altitude. This is what I say is the simplest version. All you really need to do is design your rocket, and you're trying to get to a target altitude. I know it says 1,250 feet, but this is not going to end up being the final target. This is an old number because we used to use thinner body tubes, but around last year, we decided to go to some thicker ones that are 3 inches in diameter. And so the rockets naturally got bigger, heavier, and have less altitude. It's going to hover, I imagine, more around 900 feet, but we'll give you guys more details at a later time once we decide, what actual numbers you have to go to for the altitude. And the egg protection system, not only do you have to try and meet that target altitude, but you'll also have, you'll have a capsule, a little cylinder they're going to put inside of your rocket. And in that, you're going to have to protect an egg, okay? So you can have your big rocket, an egg inside of a capsule, and you're going to launch this rocket. It's going to come back down, and you have to protect the egg inside of the rocket. And based on, how well your rocket flies, how close it gets to the altitude, plus if your egg survives, maybe if it cracks, you get less points. Or if it is completely destroyed, it's not very good. There's a little point system. It's more to just encourage you to, try to optimize your rockets, but it's not necessarily, this huge big deal. And then for the lander challenge, that is what the gold division was, marked previously. The way that works is you're going to have your rocket, and inside of the top of your rocket, instead of this little capsule that stays inside, you're going to have a capsule. You're going to design legs, have a parachute on top, and that's going to pop out of your rocket mid-flight, and it'll land separately from the rest of your rocket. The lander challenge is definitely the most time-consuming, it is the most challenging, but it's a very rewarding project to do. Actually, let me check the next slide here. Yeah, this is a great example here. So this is an example lander, what one team previously has built. So you see, this is the capsule here. It's flush with the body tube of the rocket. And then whatever else you do, totally your choice. The way that the legs are, this little rubber band thing, parachutes and all, that is completely your choice on how you build your lander. And that is, of course, a part of the challenge. I see now that the target altitude is slightly inconsistent. Don't worry about that. We'll give you more details later on. But it's still the same thing. You're going to have an egg inside of the capsule that you're going to have to protect inside of this lander. And I'll explain how the lander will separate from the rocket in later slides once I explain motors and all. I guess I'm going to stop here. This is a little important. Does anyone have any questions about the challenges? Am I going too fast and confusing, or do you guys kind of get the gist? You choose, yeah, that is, yes, actually, you can choose whatever you want to protect your egg. You will get, basically this is a coupler here. You're going to get this little thing, and the rest is up to you. You can use peanut butter, packaging, peanuts, straws, I don't know, anything, whatever your team thinks is best. Yes, okay, so yeah, I can go over the high power motors. The way that the L1 certifications work is you need to have done rockets before, preferably doing Rocket League first, just so you have some experience with rocketry, because we can't help you with your rocket when you're doing a certification. So if you have not done Rocket League before, we will not really allow you to do the L1 certification, because you basically need to prove that you alone are capable of building a rocket with a really, really big motor inside. So if you have done rockets, you have experience, you can talk to us, and if we believe in you, we will allow you to go for the level 1 certification. That's something that we'll just do on sort of a by person basis, just because the general population, usually people will do Rocket League. A lot of freshmen and stuff come in. They've never done this before, so they should stick with the smaller rockets that they can do with the help of other people. So yeah, there's no more questions about.
I have a question.
Yeah, go ahead.
Okay. So basically, would it be one person works on each part, or like that team works on each part? Like
that is completely up to you. The way that your team dynamics go is that was my bad. The way the team dynamics are is really at the discretion of the team. We're not going to tell you guys how you're supposed to distribute work or anything. We're going to give you your objective, your project. Well, we're not going to give it to you. You'll choose. You'll choose your objective. You'll either pick your team if you know people, or we'll give you a team if you don't. And then from there, you're going to meet with them, decide what everyone's going to do. I would suggest that everyone tries to at least dabble a little bit into all the aspects. So like trying to design an open rocket using SolidWorks and building, just so you can kind of get a general gist of the whole design process, especially if you want to do your level 1 certification, say in the next semester after doing Rocket League here. You're going to want to know everything, right? since you're going to do it alone. But no, yeah, we're not going to tell you how to, do your team.
Okay, thank you.
Any other questions? I see chat. How long does it? It's a semester long. It actually, once you know how to do rockets with Rocket League, you can do it in a semester. That's how long it took me. So yeah, you can get your high power motor certification basically in a year if you do Rocket League now and you're successful, and then you do your certification next semester. So yeah, that's how long I would say. Any more questions? Once, twice? Okay. If anyone has questions, of course, feel free to ask, and I can come back to this, but I will be moving on. Okay, so this is our tentative schedule. We know the meet times. We do say subject to change just in case some crazy stuff happens. Week 1, that's today, and this past Tuesday. This is just super basic intro stuff just to kind of get your brains ready to go for rockets. Just basically to understand the concepts. That's what college is all about, trying to understand the concepts and stuff. We're teaching you the concepts now so that once we go to the actual designing and building, you're really ready to understand why it is you're doing what you're doing. So that's what this week is all about. Week 2, it's about using OpenRocket. So make sure that you have OpenRocket downloaded, because one thing I would suggest is that during the meeting, whether that is today or if you somehow make it Tuesday the next week, it's nice if you could try to follow along. So the way that the OpenRocket and even the SolidWorks basics classes work is we're going to have these programs open and we're going to be doing the process in front of you guys. And so it's really nice if you follow along so that you can click the buttons yourself, do the changes that we do, just so you can get ready so that when you're doing the project yourself, it's very easy for you to start just going off and designing your rocket and using SolidWorks to get your parts ready. So it's good to have OpenRocket for week 2, and then week 3 it's for SolidWorks, and then week 4 it's build times. That's when it starts. Don't freak out. You'll have much longer than a week to build your rockets. This is just when build times start. And when we say build times, it's really just the teams are free to collect their parts and build because they're ready to go. Not that you have to build from this day to this day at this time. So yeah, that's the current schedule and what we're looking at. Okay, so let's go to the fun part, which is how rockets work. Now, I'm sure a lot of you might have some ideas about this part. So I know this might be a little bit boring, but I'm still going to go over it. So what makes rockets move? Well, it's Newton's third law. It's that for every action, there's an equal and opposite reaction. When you punch a wall, it punches you back. And well, the rocket motor does the same thing. You push mass down, and that's this part. Take matter, solid or liquid, you burn it, and you turn it to gas. And then that gas builds up pressure inside of this combustion chamber. And then the gas is pushed down eventually through a nozzle. And then as it goes down, your rocket gets this reactionary force upwards, so your rocket flies upwards. So that's the basic gist of how rockets work for anyone who didn't know. Who wants to see chat? Hold on. Hey. Yeah, no, Kerbal Space Program is very good. You guys should get it if you can. So that's the motor. The motors that we use is this long-term, the ammonium perchlorate solid rocket motors. Basically, the solid motors are kind of like the space shuttle boosters. You know how you have this shuttle where it's like the airplane part, the giant orange fuel tank, and then the side boosters. Those were solid fuel. And so that's what we use. And so the way that it is, it's a single-use reloadable. Basically, you have this motor, you have a little motor tube in your rocket, which we'll explain in future meetings. But you basically take your motor, shove it in the tube, you ignite it, and then it goes. And that's the only time it's used. Once it's gone, it's done. The motor dies and you never use it again. So the advantages, they're very easy because as I just said, you just put it in, ignite it, and it goes. Hey. Great availability. It's very widely available, and also low initial cost, because there's multiple systems you can use, like there's hybrid motors, liquid, all these really crazy complicated things, but solid motors are very, very cheap for the first time that you use it. The disadvantage is higher recurring or like per flight cost. Basically, if you were to have a rocket and just launch it once, which is what we do at Rocket League, solid fuel, perfect. But if you're going to take a rocket and launch it multiple times for whatever reason, solid fuel ends up building up on cost, because if you were to take some other system, all you really need to do is refuel it, which is something that you cannot do with the motors that we use. Regulations, they can, there's a lot of regulations on stuff like solid fuel. And that's why there's also certifications because of regulations and all. And propellant age constraints. What this means is that when you take your motors and you don't use it and you're just like, I'll just stick it in the damp closet. Over time, these motors can go bad. So you can't necessarily store them forever. So it can happen where you'll have this old motor, put it in and it's dead before launch. So you kind of wasted your money there. How the solid rocket motors work, it's very interesting. So these diagrams are really, really nice. Let's do this because it isn't burning yet. This gray part is metal. It's just the nozzle. Blue is propellant. Then there's this green delay and ejection charge, and the retainer cap just keeps it all in. So this part makes sense. The propellant, it burns, gas goes down, and your rocket flies. I'm sure everyone understands what that's all about. But then you have this ejection charge and a delay. So what happens is that after the propellant is done burning, the fire doesn't go out yet. Instead, there's this delay here that's made up of different materials to basically cause the fire to keep burning until a specific time. So like a certain number of seconds. Then you have an ejection charge, which doesn't go down. It explodes up into the rocket. And the reason why is because in your rocket, you can imagine you have this rocket. I don't have any demonstration rockets on me, unfortunately. But inside your rocket, you're going to have this cord called a shock cord. And your rocket is either going to split in half and have two attach points, one on the bottom, one on the top. Or it'll split on your nose cone. I shouldn't go too far, but you'll have your nose cone that can go off, or your rocket splits in half. And on the shock cord that keeps everything together, you're going to have your parachute. And then your parachute goes out and can deploy later. So that's what the ejection charge is ultimately for. It's to deploy your recovery system. So that's why you have this sort of counterintuitive, like, why would I basically explode my rocket? And the reason why it's because you need to do that. And also for lander people, this is how your lander is going to detach from your rocket. It's going to be inside. It's going to burn out. And then once the ejection charge goes off, that gas is going to push through your rocket onto the bottom of your lander and then push out. Your lander is going to push the nose cone out of the way and just fly out, whatever velocity it does. So that's how the lander actually works. And then for altitude and payload, we just cut in the middle. It's very easy to do. So yeah, that's how the solid motors work for these smaller rockets. Rocket motor designations. So this is actually the motor that we use for you guys in Rocket League. For the L1 certifications, we use bigger motors. So the way that these little classifications work is there's three main components. There's this big letter, little numbers, dash, and then another number. this letter here, it's like a general range of impulse. So the way that the letters work is that each letter up is twice as powerful as the one before. It's like a B motor is twice as powerful as an A motor. The highest you can go without a certification is G, which is what you guys use. The L1 certification allows you to do H and I motors, which is addressed down here. I know I'm not really following the slide, but you know, I'm getting ahead of myself, but that's what all this is showing. So that's the letter for impulse. This little number here is just the average thrust for that particular motor. And then this number here is the delay. So you have this G74-9. So it's a G motor. The impulse is 74 newtons times seconds. And there's a 9-second delay between the propellant burning out completely and the ejection charge going off. So that there's this 9-second delay between those two. And this is just an example here with a J motor, which is a really, really big motor. And then, yeah, this just shows what I said. Cool. All right, now we're going to talk about rocket stability, because your rocket is going to fly up, but you want it to fly up and not do this and eventually go sideways and then down. So you need to make sure that your rocket is stable. So to do that, you need to know these terms here. Two big key words for rocket stability. Center of gravity. I think a lot of you guys know this from, previous years. It's that thing where you take an object and, you put your fingers closer and closer to a midpoint somewhere where it balances. That's your center of gravity. And the reason why that's important is that whenever your rocket rotates, it's going to rotate around that center of gravity. I have a bottle. This is a rocket now, right? You have your body. This top part is a nose cone. The center of gravity, you're going to want somewhere up here. So you can imagine that when the rocket is exposed to forces, it's going to rotate around that. And you want it to do this again, to be stable. So that's why you need to know where your center of gravity is. And that CP center of pressure is where the aerodynamic forces act. Later slides really illustrate this. Okay, let me go here, just skip ahead, because I'm already on the subject of rocket stability. Okay, so you can see that there's this diagram here. The rocket is sideways like this. So you imagine your rocket is going upwards, and then something happens, either because the manufacturing is slightly off, so it naturally tilts one way, or a gust of wind pushes the top and it goes like this. Your rocket's traveling upwards, but it's sideways. So you have your wind dragging down like this, okay? So there's all these aerodynamic forces along the side of your rocket. You can average all that out to the center of pressure, which is going to be this right here. Your center of pressure is going to be kind of down here. So you imagine your center of gravity up here by the top, and you want your center of pressure down here by the bottom, okay? And the reason why it's the center of pressure is on the bottom is because you have your fins, right? You're going to have 4 or 3 fins along the sides, which is going to create a lot of drag, okay? So what happens is that when your rocket kind of tilts to the side, you're going to have forces going down here from the side, and you can have 2 components. I don't know how many of you guys are familiar with resolving forces into components, but basically imagine if you have an x-axis going along the top here of the rocket and then y perpendicular to that. If you have this angled force here, part of that is going to go down like this along the rocket, which is going to be like a drag force. And then another part is going to be to the side perpendicular. And the reason why that side component is so important is because on average, it's going to act down here. And what's going to happen is it's going to generate something called a moment. Now, if you guys don't know what a moment is, it basically will push this sideways, okay? So if your rocket's sideways, you have a force, it's going to try to generate a moment. And the magnitude of that moment depends on 2 things. The magnitude of the force applied, so how big this aerodynamic force is here, and the distance from where that force is to basically where the pivot is, which is your center of gravity. So a huge part of rocket stability, I think the next slide. Okay, yeah, this is nice. I'm sorry I'm going out of order, but these slides help me out a lot. So basically the distance here will increase how strong that force is to restore it back straight. So that's why you want to know where your center of gravity and pressure are. The further these 2 points are, the stronger that restorative moment is to push your rocket back straight. So that's why lengthening the body tube is one way to make it more stable, because the longer your body tube, the further away these 2 points are, and the stronger that moment is. Okay, so I've gone really in a big tangent about rocket stability. Does that make sense to everybody? I know it can be really confusing, especially because I really do go on the technical side of how it really works, because I want you guys to understand what's going on with your fins. Okay, cool. That's great. Okay. Yeah, no, so that's basically what this slide is talking about. This slide really helps demonstrate too why it is so important for your center of gravity to be on top. Because an unstable rocket, if your center of gravity is here, but your center of pressure is somehow here, when your rocket, oh wait, hold on, let me see chat. Okay, cool. When your rocket kind of goes to the side, if your center of gravity is here, but your center of pressure is here, when the force goes, it's not going to restore. It's going to go in the same direction as the rocket as it's going. And so it's just going to flip like this. And that's bad. If your rocket does this mid-flight, you did not build it right or design it. So that's why you want your center of pressure to be below your center of gravity. I said it backwards, center of gravity above pressure. Keep this in mind at all times. Okay, so if everything makes sense to everybody, I'll move on to fin design. Fin design is really important because, well, all rockets have fins for a reason. And so there's a few terms that you're going to need to know when it comes to fin design. The root chord is basically how big the fin is from tip to tip up here. So like imagine if you have a fin kind of like this, your root chord is going to be where my middle finger and thumb are. So it's just that big length down there. The tip chord here is just the top. So basically where the palm of my hand is, if the fin is like this. You have your fin height, which is how high above the body of the rocket it goes. So if the length of my thumb plus whatever else to my palm. And then you have the sweep length here. Basically, if you have like an angled front here, you'll have this sweep length, which is going to be the distance from this tip here to the top of the tip chord here. Not necessarily the distance of like this diagonal here, but the horizontal distance from this tip to this part. Okay. Then there's this weird thing, which is a fin tab. The way that fin tabs work is they actually go inside of the body of your rocket. And the reason why that is because on the bottom of your rocket, you're going to have a lot of important components, that being where your motor is and where your fins go. So the way that the bottom is that you're going to have your body tube. Inside of that, you're going to have a motor tube, which is where your motor will go. And you'll have centering rings to hold all that together. And by the way, this is going to be a very crash course style because we're going to explain this in a lot more detail in a later week when we do building. But basically, have this tube that's secured in your rocket, and the fin tabs are going to go inside and hit your motor tube. And so what you can do is you can glue the bottom of your fin tabs and glue it onto your motor tube, and you can glue the sides onto the side of the body. So it just gives a lot of nice attach points, and just it's a lot more stable than just having like this flat edge stuck onto the side of cardboard, if that makes sense. So that's why your fin tab is here. Yeah, I don't know why these slides are so misordered. I'll go back to this later. Fin design. Okay, so fin shape, it's actually not so crazy important. So long as your rocket does end up stable, you'll be okay. Some of the nice designs for rocket fins, you have this trapezoidal. I've used this before. It's really nice. You can have a tapered sweep, but you shouldn't sweep it too much because this can actually leave your fins prone to breaking. Not that you shouldn't do it at all, but just don't make it so crazy swept that we start getting concerned. And then also a clip delta, it's this straight edge back here and then a front on the taper. But having this shape, you shouldn't have like straight square fins. We don't usually just do straight squares. We like to have that taper just so it's kind of like an airfoil shape-ish to reduce drag. What's the next one? Nah, we'll talk about that later. Yeah, sorry for misordering. Just to go back to rocket stability, after all that we talked about CP and CG, in open rocket, you're going to see a number called stability. And this is based on caliber, which is one body tube diameter. So in open rocket, you'll see a number. We'll show you where it is. And it should be from 2.0 to 2.5, okay? If that number is there for stability, your rocket is good. You have a nice, stable rocket. When it flies, it will be able to restore itself successfully. If this is too low, as in you're like on 1.95 or whatever, your rocket might go topsy-turvy. We will not like that, and we will tell you to change your rocket. If it is above 2.5, it's not that it isn't stable. It's almost like it's inefficient. So let's say if you're above 2.5, like you're at 2.7 or something, your fins might be too big. They're producing unnecessary drag. They're too heavy, and you don't need that, right? To make your rocket stable, you can make them smaller, have it fly higher, and still be very stable. Or let's say you add mass somewhere that you don't need, you can just take that out. And 3 ways to increase the CP-CG margin, which is one thing that I really want to address to you guys. Basically, if, let's say they're too close, like you have your CP here, but your CG is somehow here, not very far. You know, you want it up here, but it's down here. Well, what do? Length and body tube is tough because we give you a set length for your body tube. You can make it shorter, but let's see the chat. CP, that's an open rocket. That the program will give you where your CP and CG are. So you don't have to like go out of your way, do all these crazy calculations and stuff with your rocket. The program will tell you. It's just more, as I said, it's more conceptual. You know what I mean? You're not actually going to need to do anything hard when it comes to CP-CG. It's just so you know where stability is coming from. Because I don't want people asking, well, there's stability, but what's that mean, right? What's stability? And that distance between CP and CG is what that means. So don't worry about having to do this crazy stuff to find CP. Yeah. Once we explain open rocket, all will make sense. Just take this as a lot of conceptual stuff. But the CP-CG margin thing is good to know. So length and body tube, don't worry about that. You're not going to do that. The first 2 parts, very, very good. Add more weight to the nose. So if you have your CG very low, like this, your CG's here, your CP's here, you need it to change, what do you do? Well, you can bring the CG up and you can add weight to the nose. So imagine you'll have this plastic nose cone we're going to give you. And what I've done before for my level 1 certification is I took these like copper BBs, and this could be any mass component. It could be, you know, like what I did with copper BBs that I had lying around. Well, yeah, of course. I'll make sure that the slides are up. And also I'll figure out a way to get it on the video on YouTube. I'll just have to ask the eBoard if I'll do it on their YouTube channel or whatever. If I'll do it on mine, I'll update you guys, but you will have access to all this stuff. So don't worry. Okay, back to what I was saying. Mass components, right? You can have anything that's just kind of heavy up here. And what I use is epoxy. Okay, it's basically epoxy. The way that it works is I have like 2 bottles and they each have like halves. And when you mix them together, they'll basically do a chemical reaction and harden, okay? So what you do is you stick all these copper BBs in the tip of your nose cone, and then you put epoxy all in it to secure it, okay? And what that does is when you put all this mass right on the top, your CG goes from here and starts shifting upwards. And we'll show you in open rocket how you can determine how much mass you need to put on the tip of your nose cone in order to make it stable. It's actually a very simple process once you learn how to do it. One thing to keep in mind, and I will reiterate this once we go to building and all, epoxy is hot. When it reacts, it becomes hot. When my dad and I were testing it, we used a little plastic cup and we put the epoxy in and thought, what could go wrong? And the cup started melting. So that's very concerning. So whenever you use your epoxy on your nose cone, make sure you have like a nice bowl of ice water or a very large cup. Submerge the nose cone in that water and then pour the epoxy in and like leave the nose cone in the water for a little bit. Just to allow the heat to kind of dissipate into the water so that you don't, wreck your nose cone. Another way to increase the CP-CG margin is to increase fin area. So basically, instead of having smaller fins, you make them bigger. And naturally what that does is you will increase the forces that are caused by the fins. So instead of the forces on the top of the rocket being so dominant, basically add more force to the bottom. So your CP will naturally go down. The only thing is that if you do increase the weight of your fins, you will also bring your center of gravity down as well. So it might not be the most efficient way to do it, but I'm sure you guys can make it work. So that's how you try to fix your stability. If after all your designs, your stability still isn't working somehow, that's how you fix it. Okay, so we did fin design. Now let's do deployment. So this is all about recovery. Let me check my time. 7:06. Wow, we got a lot of time. Cool. Deployment. The way that it works, I've been telling you all about these parachutes, and you have your ejection charge, your rocket splits up either at the middle or the nose cone, and there's your parachute. Well, there's two ways you can go about deploying your parachute. Single deployment means that the moment that you have your ejection charge go off, your parachute just unfurls and just does its parachute thing. This is bad. Okay, your rocket is going to be way up in the sky with its parachute already deployed, and it's just going to start drifting because there's going to be all sorts of winds. And even if there isn't a lot of wind on the ground, there could still be some wind higher up in the atmosphere. We're going up a little bit high. And so you will be drifting for a while. You can see here on this little simulation here, 3,000 feet. We launch a very large barren field with tall grass. So have fun looking for a rocket, basically. But we don't do that. We do dual deployment. The way that works is we have this little device called a chute release. And the way that it works is you have your parachute, you fold it up nicely, you put it against this electrical component, and there's like a rubber band with a pin on the end. And you clip it. And what the chute release does is your rocket goes up, your rocket splits apart, but the chute release holds the parachute closed. And so your rocket falls without a parachute. So it'll fall kind of fast-ish, but then at a certain altitude that we specify, it's going to be like around 400 feet. Your rocket's parachute will just deploy because the pin will let go. The parachute will be able to deploy because the rubber band will not hold it anymore. And so the parachute goes off and it falls down more gently. So instead of it drifting for miles on miles, it'll fall downwards more. And then when it's close to the ground, parachute goes off when it's actually needed and will help your rocket fall safely. So we'll handle the electronics and all for you guys, but this is just a fun little tidbit on how rockets work. When it comes to painting your rocket, we encourage painting your rockets. It makes it look nice. On the picture that I had earlier of myself, that was my L1, and I painted it bright orange. When you're painting your rocket, this is a camouflage rocket. Don't do that because if your rocket is camouflage and you can see all this nice green, this brown on the grass, when you go out looking for your rocket, you will not find it because it will naturally camouflage. Another tip that I almost failed to follow, don't paint your rocket blue and white because the sky is blue and white. So when you're looking up at your rocket after it flew and you're looking to see where it is so that you can go and recover it, you got this blue rocket against the blue sky, you're not gonna see it and you won't know where to go. Not to say that you can't use green, brown, blue, whatever. Include some flashy colors, orange, red, maybe yellow, neon colors, maybe some stripes or dots, whatever, just to help your rocket be seen, even if you have some of these, more camouflagey colors. Does that make sense? Yeah, I think that's a little more simple compared to the stuff before. Due dates, this is all still pending. I'm sure a lot of you have already got your interest form in. Okay, so OpenRocket will also tell you what that is. OpenRocket's amazing. It will just tell you everything. It will give you an estimated apogee. Apogee is just the highest point in your flight. But also on launch day, we'll give you guys, we'll attach an altimeter into your rocket, and that will be able to read what altitude your rocket actually went. So you'll have an estimated height from OpenRocket, and we'll have your actual height from an altimeter. And going back to the objectives where it's like, oh, you have a target altitude, that's how we'll know how high you went. You have this altimeter in it. This is all pending. Sorry that we don't have all this together. It's been a very interesting semester trying to do mixed mode for the first time. But we will, we'll send a bunch of announcements to you guys whenever you guys need to know something. I imagine that objective signups will be next week. That's what I'll try to do. And then we'll do team signups. And then we'll do these at a later time. So yeah, no, be posted, be ready. Tentative launch date. We haven't pinned down the launch day, but usually we go to this place, Senshi Port, Palm Bay. It's quite a ways away, but it is one of the only places that is the middle of nowhere, and I mean it. And they usually do launches every third Saturday of the month. So this will be somewhere in November so that people are still sticking around on campus, because if we do it in December, it might be, winter break and people are out on vacation, but we'll let you guys know. Okay. There's a lot of still kind of stuff up in the air. Software, this is just links to software if you guys don't already have it. OpenRocket is this. You're going to need Java to make, chat. Even if I can't really participate, can I still learn? Yeah, just keep coming to the lessons, dude. And yeah, you're free. I'm not going to kick you out like, you're not going to build Rocket, disgrace. No, it's fine. Just stick around and check out what the program's all about, because they're really easy to use. And SolidWorks is a very daunting product or software to use. But with the way that we use it, it's actually very simple. Anyways, OpenRocket, make sure that you have Java downloaded to make OpenRocket work. Otherwise, it will not. And then SolidWorks is on here. Follow the instructions for SEK, not SDK. And also get the most updated version. I know that someone asked a question in the Rocket League chat. And yeah, just get the 21-22. Yeah. Any questions, guys? Because this is basically the end of the meeting. I've gone over everything that I wanted to. Ooh, chat. What's up? Can we? Ooh, I don't think so, actually. I think it's only the fun engineering stuff, but you can do a Google search for, wait, why is Java needed? Oh, okay. Java is just basically how OpenRocket runs. So if you don't have Java on your computer, OpenRocket will not be able to run. And then can we load Java from CCS? I don't think so. I've never seen Java. Yeah, all good, Tyre. But I think Java should be a very easy thing to find. Just Google Java download and just go on the Java website. If you guys need help downloading Java, just send a message. I know so bad of us. We didn't actually help you guys out with that. So how many rocket parts are going to be standardized? Okay, so that's actually a great question. Let me answer that. So the way that it works is you're going to have a bill of materials. I've been talking too much. Let me drink water before I do it too much. Okay, so the way that it works, you'll have a bill of materials. It will be like this Excel spreadsheet, and it will tell you all the parts that you have. So honestly, pretty much all the parts, you'll get like something generic. Like you'll get this big body tube, nose cone, 2 sheets of plywood, which you'll cut your fins out so you can totally determine your fin shape. And then, a certain amount of cord as your shot cord, things like that, depending on your project. So there are some things like the body tube is standardized, the kind of wood that you use is all together. I'll answer your question in a second, once I'm done with this. But basically, you'll have some standardized parts, but you're at liberty to use these parts however you'd like. For example, the body tube, a team has cut in half and produced a stable rocket. Sure, if you want to cut your body tube in half and still do well, go for it. Produce a nice, fast rocket. And your fin shape, completely up to you. So you're at a lot of liberty when it comes to how your rocket is going to come out. I hope I answered that question all right. I know it's not the most detailed answer, but that is also something that we address later on. Once we talk about building your rocket and stuff, we'll talk about the parts and what you get. Do we have to buy OpenRocket and SolidWorks? No, OpenRocket is free, just completely free online. And SolidWorks for UCF students like us is free. As long as you go on the my.cecs.ucf.edu, you'll be able to get it. Just a little tip, by the way, for this website. Sometimes you'll have password problems. You have to scroll down a little bit. It doesn't look like you can scroll down in that website, but you can. And there's an email that you send a message to and say, hey, I'm having, password problems. Please reset my email. I know it took me way too long to figure that out. But yeah, no, it's completely free, guys. These software, it's completely free. So don't worry about it. All right. Any more questions for this meeting? Because if not, then you guys are free to go. I think now what I'll do, I'll go ahead and stop the recording. And yeah, no, I appreciate everyone coming out, by the way. I should have said that. It's really nice to see. There's a lot of interest around this project, actually. You'd be surprised. There were like 40 people that showed up to the in-person class on Tuesday, which is mind-blowing. Yeah, of course. It's fun. It's actually like a passion of mine. So I definitely enjoy teaching you guys how to build rockets. So it's really nice. Yeah, let me